Okay, so let's look at number 5. It says, set up and evaluate the integral that gives the volume of the solid formed by revolving around the x-axis. So I know this is a two-dimensional screen, but just like we did with Desmos, you're basically going to pull this area out where it does revolve, similar to the one that we did over here, right here. You're going to pull it out of the page, and it'll rotate accordingly as far as what we showed in class, okay? The way it rotates about the axis, okay? So let me see if this will allow me to do it. Yeah, maybe. So as you rotate it out of the page, it's going to revolve around that x or y is equal to -1 axis, and so on and so forth. It's going to create that three-dimensional piece, okay? So let's go back, and we're going to pull this out of the page and rotate it about the x-axis. So you have to make your decision right here. If I rotate this around the x-axis, first of all, rotation, you have two choices. You have a disk method or a washer method. Okay? And remember, washer methods are the ones that have that void in the middle anywhere throughout the entire interval. And disk methods, they don't have a void. There's no emptiness in the middle anyway. So what would this be, washer or disk? This would actually be washer, because when you rotate this around and you create these circles, there's going to be void that exists all right there. There will be no shape there. There will be no actual density volume there. You with me? Okay. So, being a washer method, we know that the washer method, okay, let me go ahead and do this real quick. The washer method has this bigger circle, and it's going to be subtracting the smaller circle, if you will. So there's the bigger circle. It's subtracting a smaller circle. So those washers are going to look something like this as you go throughout the entire problem. Okay? And the equation of this is the big circle's area minus the little circle's area. What can I GCF from this? Pi. So the equation that I want you to be associated with the actual washer method is big R squared minus little r squared, and it's going to be pi is going to be pulled out, whoops, squared, and pi is going to be GCF'd out, so where you just have to work with it once. Okay? So far. Let me highlight them for you. Big R is going to be whatever we determine it to be right there as a function. Little r is the little radius. When I say little radius, here's little r, and you could have gone up or down, and here's big R. You see how I'm doing this? Okay. With this in mind, let's talk about our bounds. What is, oops, let's do this in gray. What are the bounds that we will integrate when we're looking at this cross-sectional area? 0 to 1. So 0 to 1, is it dx or dy? You've already made a decision. Dx, because they're vertical slices. Now here we go. And guys, what's cool about this unit is a lot of it is repetitious. Once you understand how to set one up, you pretty much can do a bunch of disk method problems. But you have to be very methodical and consistent with what are the steps that you're asking yourself to make it easy. Okay?
To find 0, 1, did you do the y-axis?
So to find 0, 1, we're taking vertical slices. So we're saying where the intersection occurred between the x-axis and the function, and then just this vertical representation as far as going all the way to 1.
So if it was going horizontal, it would be the other way.
Correct. Well, if it was going horizontal, you'd be looking at y values.
Yeah.
Okay? So here we go. I need to determine from the picture, and I'm going to see if I can draw this as best as I can. I'm going to draw this washer method the way that you see it over here off to the right. Okay? So here we go. It's going to come out of the page, and then it's going to go back behind the board, and it's going to be way over there. The bottom function will come out of the page, and then it'll go also back behind the paper. Let me do that dashed line a little bit better. It'll go behind the paper. And the shaded region that exists in between of these revolution pieces is going to look like that.
Where did that little, like, square come
So what that square is representing in WebAssign, it's representing this width that I keep showing you whenever I turn the circle to the side and I said, what is it that you see? And you said a line. That's what it's representing. It's representing each infinitesimally small widthwise rectangle that we can see as a line. And y'all said it itself. What is that width of that line trying to approach? 0. Okay? They just enlarged it so that you can kind of understand it's going to be a big minus the top and stuff like that. Okay? So here we go. Let's look at big R. Big R is from here to here. And here's what I'll say, guys. The biggest advice that I can give you to make these easier is you always go from the center of rotation. This is called the axis of revolution. And you're going to go from there, and you're going to go out to the biggest R value that you see. In other words, you're going out to the furthest function away from that axis of revolution. Let me show you what that looks like over here. X-axis, if I go out, I will stop whenever I get to the most outer function piece. Okay? And what I just drew right now, from the x-axis to that function, is big R. Any questions before I continue?
So basically it's the same thing as we were doing in day 1.
Yep.
Where's the top function minus the bottom?
It's a lot of day 1, top minus the bottom, but instead of integrating a line only, this line is actually area, if you were to look at it from the cross-side view, if you will. And if you integrate area, you get volume. Just like if you differentiate volume, the volume formula for, let's say, a sphere is 4/3 pi r cubed. And if you were to differentiate that, you get 4 pi r squared, which is the surface area of a sphere. So the derivative of volume is surface area, or area. The integral of area is back to volume. Okay?
Is it like really important that like we're able to like see like a disc or washer like in any like graph?
Is it important that, and that's the hardest part. That's what a lot of people say, is that they can't see that this is the front popping out and then it goes back behind. This is the front popping out. If you can't see this, it's okay that you can't see it from the graph here, but you have to determine, is it washer method or is it disc method? And then if you want to draw your picture like this, that's fine. Y'all with me?
Can you do number 7?
Well, let's finish 5 first.
Or not.
Yeah, we're not done. Alright, so here we go. Let us go ahead and now input. Look at this. We're looking at big R. We're looking at the green line. Now, just like Chris said, from day 1, we're going to look at this green line, and I want you to tell me the length of the green line. How long is that green line? What do you do to determine the length? You're doing top minus what? The bottom. As far as the top minus the bottom, if I asked you to tell me what function is the top function, what would you say on this? X squared. X squared is the top function. What function is the bottom function? So again, I'm right now looking. This is where the confusing part comes into play. I'm trying to determine the length of big R. So I'm really only looking at, let me highlight it in red, from here to here, that wise. So from here to here, that's what I'm looking at, as far as what is that distance.
So you only 1%? No, you don't.
So it's just 0. Like, do you have to put 0 in this case? You don't, but I need you to get used to putting that number there, because what if we weren't revolving around y is equal to 0, or the x-axis? What would we do if we were revolving around y is equal to negative 1? You see what I'm saying? So we have to account for that bottom function, even though it's 0. Because I want you to get in one consistency, not have all these what ifs, you know what I mean? It's almost like doing quadratic formula. It takes forever, but I promise you, you're going to get the answer. So, and with practice, you'll know what you can trim off. Okay? So the top function is x squared, and the bottom function is 0. The next thing that we're now going to do is concentrate on this blue radius from here to here. Okay? And that's right here to here. And if you have to do two little diagrams to kind of see how does it correlate to your graph, like Carly was saying earlier, that's a little difficult to see, by all means do so. Alright, here we go. We're looking at little r right now, okay? What's the top function of little r? X to the 7th. And we're going to subtract the bottom function of that little r. What's the bottom function? 0. So from here, because of the fact that it was 0, here's where people make mistakes. Sometimes what are important right here to help you with mistakes throughout this is that these parentheses, they're important. Okay? Because you could have big, huge functions in there that have negatives, that especially these two right here, if you're subtracting a negative, it could throw the whole thing off. So over parenthesizing, there's nothing wrong with that. And that might not be a word, but you know what I mean. And the same thing here, we could put parentheses here.
Is that a formula that you could just memorize?
Oh yeah, this is the formula, like whenever you
The
just...
lower one. The one where you just work on.
This one? Yeah, you can memorize that.
Oh.
Pi of the integral of big R squared minus little r squared. The hardest thing, guys, is just realizing what is big R, what is little r. Okay? Any questions on this? And yes, this is a lot of it is calculator, okay? To where from here, it's all about the setup. Can you do the setup and then just throw it in the calculator and see what you get? If there's some that are on the AP exam and some that we will do it as practice and on the test that are non-calculator, they're not going to be these crazy long ones that would take forever to integrate, because you already know how to integrate. Okay? It's just, let's integrate by hand, work with fractions, refresh with fractions, being able to show that we could take the integral of something that we've set up as a volume. Yeah?
I can't attack it first.
So are we getting the area of the slice, or are we getting the volume of the 360?
There we go. That's a really good question. This right here represents the area of the slice. Okay? And just like we said, this area of the slice is going to change throughout the problem. It depends on how far these functions are away, and the way we showed that before looks something like this. So we had this circle, we had this circle, and we said if we were looking at it from a side view, let's see if it'll, yep, if it let us see it from a side view, and we were going through, this is what it would look like. So side view, it's like this, and let's say that as I went out, the function just got bigger. Okay, maybe this will help you too, Carly, as far as the just being able to interpret what it looks like. Let's say that we're looking at way over here at this slice right here. Look. So duplicate, bring it over here. We're going to say that this is going to be the cross-sectional slice. Let's say that it's the arbitrary one that's way over here. And they're pretty much just going to change throughout the problem. And I hope you can see what I'm doing. Throughout the problem, these slices will go small, they'll go big, they'll go small, they'll go big, as you're just going through with the integral. Because when you integrate a slice of area, you get a volume. When you integrate a slice of line, you get area. Are we good? Okay. So Plugging this in, solving it out, you should get 2 pi over 15.